the essence of this talk can be distilled into 3 words. Basically, automatic OCR correction. We're trying to do it for certain circumstances. We have a product called Overproof. That's what that writing says there. And the reason we called it Overproof is because we're considering the publication process. In the last couple of centuries, a newspaper or book would be published by somebody who would create a draft. The draft would go and be proofed, and then it would be published and it would be available to readership. In this new age, all these things are given a second life. And so what happens is you get a kind of a second draft, a digital draft of text that comes out of the scanning and OCR process. So we think that you've got a... Is it... what do I have to do? Right. Is that okay? Yes, sounding louder. I'm getting my echo. Where was I now? That's really thrown me. What point I was still... Now, where a whole lot of works are being given a second life, there's a second digital draft which is produced pretty much automatically by scanning and by running an OCR. And then some people then just put it onto the web and let people look at it. But when you do that, it's got about 20% errors. And we're suggesting there should be another proofing stage, which is automatic. And so that's why we called our product Overproof. All right, so it's just automatic proofreading and correction, which takes place before, in the second life of a document, it's digitally published and made available by search engines. And to sort of complete the introduction, we come from Australia, so I'm jet-lagged, so anything I say that's silly, that's the reason why. We're basically 2 developers, and the other one is Kent over there. Kent, please raise your hand. And we're pretty pragmatic, but we're pretty interested in the maths and stuff behind it all, and we're trying to put it all together. Kent has had extensive experience with a project many of you have probably heard of, the Trove newspaper crowdsourcing correction project, and he in fact suggested it to them and implemented it. Now, we can't correct everything, and some things maybe aren't worth attempting to automatically correct. Some things, there's so much of it that they can't be corrected any other way. So our target is newspapers. And newspapers are, in fact, the first draft of history. So I'm sure there's going to be a lot of life gotten out of those newspapers. And they've proven to be incredibly popular when they are put on the web. For example, at the National Library of Australia, they have 13 million page views per month. And they also have 85,000 volunteer corrections, 85,000 lines corrected per day. Unfortunately, that's not enough. Well, we think it's not enough because we're going to say you should be doing something else as well. So our product called Overproof is designed to just run on a normal kind of a server. We're actually putting it up on a sort of as a service, and in fact you can use it for free at the moment on short things. So it runs on a normal server. It's supposed to be, we designed it so it works best on noisy text. That is, things with a fair few errors. In other words, newspapers. We designed it for newspapers. We want it to go reasonably fast, 1,000 words a second. In fact, it goes about 2 or 3 or 4 times that fast. And our benchmark was it had to leave it with, we had to correct more than half of the errors, and we did that. I'm not going to go into a lot of architecture here, but in fact, there's 2 programmers, so we thought we'll make 2 modules. Kent wrote the top one, which is accepts documents that are delivered via a web interface or possibly just uploaded in a massive batch. These documents might be something like alto files, so they're XML of text which has been through OCR. What Kent does, what his manager triage program does, is he actually makes about, say it's a newspaper page, he makes about a dozen passes of it, looking at various things. The primary job he has to do is to triage it and also possibly suggest some corrections and or actually make some corrections and say, right, they're done because they're guaranteed surefire ones. But then otherwise, or in fact, in every case, little smaller areas of text, like about 20 words, are sent to the core module, which is the bit that I wrote, which does kind of some more nitty-gritty kind of things to produce more corrections. Both of these things have access to natural language sort of models, in other words, word lists, basically, n-grams and that sort of stuff, plus a list of corrections that may have come from perhaps volunteer correction or something like that. We actually use separate models and everything. It's all quite separate, and when I test my thing, I just stub out Kent's thing. So my thing works, does the whole thing all by itself. And when Kent's sick of mine, he stubs it out, and his will do correction as well. But together, two heads better than one, and we think we do a reasonable job. This is just to explain the interface between Kent's manager module and my core module, if you want to call it. Those little circles are supposed to represent words. They don't look much like words, I know. But the ones that are coloured sort of gold are ones which I'm representing as being triaged as, don't correct these ones because they're good. And Kent has sort of done that, triaging, using a whole lot of things like Google 5 grams and quite a lot of other data. I won't get into the sort of language models and so on at this stage, but so the reason for carving off little bits for my program to work on is that it's a hell of a lot better if you have some leverage at either end of a 10 or 20 word thing where you know the start and end are probably pretty good. Makes it easier to fix up the middle. Also, the notorious problems like columns are mainly handled by Kent's manager module, although I'm aware of them. And some corrections have been applied, suggestions are given if I want to use them, though I might not. And also, because one of the things that I mentioned, one of the things in the first slide was our title was sort of context beats confusion. Well, Kent, I'm focusing on a small set of words, 10, 20 words maybe, but Kent gives me the context of the surrounding page, like including the topic words, and also an indication of just roughly, is it a document that's bad, lots of errors all over the place, or does it appear to be a document that's quite clean, because we adjust slightly to account for that. Now, when I tell people what we're doing, they usually say, well, can't you just run a spell checker on it? And, well, we did that and it doesn't work. In fact, it makes it worse. But so the important thing with regard to that is that fixing spelling and typing errors is pretty easy, really, because there are not many types of things that go wrong. They're very predictable. But with OCR, you get all kinds of letter changes happening. That says representatives of the government, by the way. And I'm just comparing it with the next one is random, which is, I wrote a little random number thing which says, will I do something to this one? Yeah, I'll just pick a letter, any letter, put it in. So the point to make there is that there is a pattern in the OCR, and it's very important to know what this pattern is in order to decide how likely it is that something has happened as a result of an OCR going bad, or maybe it's just too unlikely because some things OCR doesn't do. So we're still talking now about the error context part of it. And we've got in memory, a sort of a large matrix which takes into account all kinds of transitions or edits that the OCR can inadvertently make. For example, if the OCR sees Rn, it might emit an M. So the cost of that, and I'll explain cost in a second, is 4,451 in our scheme. And the other way around, it's 6,652. There's even a cost for doing the right thing. So if you have a word with a W in it, because a W is a bit of a, standout word, it doesn't actually get changed that much. It hasn't got anything really similar to it. So the cost of the OCR correctly emitting a W is a very low cost, 93. But E is a little bit more fragile. So the cost of it getting right is higher. And these costs, by the way, they're negative log probability based, but there's a factor of 1,000 in there. So if the probability, if this number goes up by about 693, then it's doubled. Okay, so but this is the key to what we're doing. We're doing instead of just saying we've got an error here, one character is out. We say we've got an error here, one or two characters are out, and the first character was sort of like an easy one that didn't cost much for the OCR to make a mistake with. The second one was quite unlikely. So we're examining a pair of words now because a thing that we have to regularly do in the process of correcting is to decide whether some suggested correction is in fact reasonable. Now, here the bad word is obviously renornie, and the correct word is morning. Well, it might be, who knows, perhaps there's another one that's also a potential correction. So in deciding that, we have to kind of balance two things. We've got language models, and we have to think of them and find out how likely is it in the general context that the word morning is the right word. But in order to suggest morning as a correction for renorning, we have to make a couple of little changes. Now, they might be changes that are very likely in an OCR context. Typical things like C goes to E. It's just so likely that you're pretty happy to accept the correction. So this is the noisy channel model where you balance a language cost against an error model cost and do that with all possible suggestions you can muster and then make your decision about it. So here's that specific thing again. If we're trying to decide how costly is it on a word basis, we already know all about all the letters, on a whole word basis, what's the probability that morning would somehow be morphed into renornie by the OCR engine? And first of all, we have to use the Levenstein algorithm to actually determine that M probably changed to Rn and G changed to Y. It's slightly modified Levenstein thing because we take into account the actual costs or weights, which are those numbers in that slide before, and we also allow splits and joins of letters. So it's not just like you count up the edits and the substitutions, deletions and insertions. It's a little bit more than that. But in the end, we find the most likely path for morning to mutate into renornie, and then we give it a number by adding it up. But we do a bit more than that. Now, I would encourage you all to squint like this and have a look at that, and you should be able to make out some letters. This is a sort of imaginary font. It says CL on the left and D on the right in purple. Now, when we're comparing two words to find out can one morph into the other, what we do is we, in memory this is only, build up this incredibly simplistic set of bitmap kind of representations of the glyphs of each of the letters, and then we move it around, in our little algorithm moves each letter, just jiggles it a bit until we get the best possible correspondence. And basically, so in this case here, we'd put the purple thing over the green and blue thing and wiggle it and find out how close they were, all in computationally. 5 minutes already, okay. So to correct, you have to suggest. We have a whole lot of, because this is the most important thing in correcting, you can't go anywhere unless you can invent something which could be the correction. So we have all these methods, and one of them is based on a language model where if you've got a string of language like the Antarctic sheet, the guess is ice, and you can do that without knowing anything else. But the one I'm going to talk about is generating them, and this is a rather complicated slide for me to do in 5 minutes, but we use the A* search algorithm. What this is supposed to represent is HCII might be something that the OCR delivered to you. What the hell could that mean? Well, if you squint again, you can see it could be HEN and various things. Now, what we do is we make a list. See, underneath HCII, there's a list of possible edits in ranked order that could happen starting at each one of those letters. That's the sort of like the rules of the game. And then the game is to follow those arrows in that language tree, starting from the green. You follow and you get to somewhere, and you see how many of those edits, they're like H to LI, for example, you used. And you can actually, you've only got, like, for example, take where it's gone HEN. It's got to a word there, and at that stage, it knows the cost of that word and it puts it in a queue. It's a priority queue, so it's a best first thing. And for another one where the first thing it did was decided H could be LI, it's probably got a low cost there, and it goes into another queue because it's not yet complete. It hasn't consumed all of the HCII. And at each iteration, what we do is we get the thing which is most likely to finish with a decent cost, and then we move it along one step. Eventually, the output queue has got enough good stuff in it, and we stop, and that's our suggestion. And here's the kind of things that we actually suggest. Some people say that the most errors are only one or two characters different. Well, when we did got a ground truth, did our sort of evaluated our system, we then had a look at the actual changes, and these are genuine things. We didn't just make them up. These are that little thing with the arrows and stuff that I was just talking about. They are that produced these as top suggestions. So Knuplu is company, and is railways, etc. So we felt incredibly happy about that because we can clearly correct some quite long things, and we didn't even blow up the computer. We achieved our speed gains. Now, well, that's not the end of the game. We've got to do one more thing, and for each word, or actually combinations of word, we have to work out how to join them all up. Like over there, we've got unsichtlich, which could be unsightly, unseemly, unsettled, and so on. All these things were things that actually we encountered in errors. We didn't make them up, except I put the sentence together, because it's so unlikely to get two unsettlives there. But I did it just for the teaching purpose, basically. So anyway, the red is what we think is the best line through that. And you can see it's non-trivial. We use a simulated annealing program process there to improve it after an initial simple beam trigram search. I'm racing through here. I'll pretty much skip over this, but in I think the second slide or third slide, we had models. These are sort of like n-grams and all that sort of stuff. And this is just to say that, yeah, we can change them. I'll go on to the next slide now. Testing. 1 minute, I'm making it. So testing was a real hassle. We had to produce some ground truth. Other people have mentioned ground truth, and we have a real hatred of ground truth now because we found we had to do our own ground truth. We tried to sort of get some from stuff corrected in the National Library of Australia corrections, which are publicly available, but actually humans are not perfect, and so in the end we had to put the hard yards in ourselves, do a lot of work, and we got some ground truth, and then we ran our system on it, of course, and did a whole lot of counting, as you do on types and tokens and so on. And the headline one there, we got 70% reduction in the word errors. But we did it 3 ways. There are 3 types of ways you can count. One is where tokens, one is types, and another one is when we did a log entropy weighting to sort of simulate what some search engines might do. Now, it's Sydney Morning Herald there, that's what SMH stands for. Now, that's an Australian thing. Some of our training data is Australian-centric. We didn't actually test on our training data, I promise. However, there's still an Australianness about it. So we tried it on US newspapers, and we got, guess what? We got slightly not as good results, but they were all within, we achieved our goals. We got 65%, for example, on the raw error rate. Finished. Yes.
Yes. Just a minute.
I just want to make sure I understood how you initially populated your Levenshtein cost matrix. That was from the bitmap shifting? Your initial confusion cost matrix?
How we got the cost matrix was, well, we did it several ways. One was actually a bit like what you might have in mind, that we did physical, geometrical similarities between things and so on. But then because we had a lot of data from the human correction, we just have pairs of sentences, and then we have a standard thing which runs through them. It essentially counts all of the occurrences, smooths some things out. The ones that involve double letters, we have a standard set of double letters because it would explode into hugeness otherwise. So,
John, can you use the microphone?
The other thing I was talking about, I didn't quite finish it actually.
Can you use the microphone?
Oh, sorry. The other thing you mentioned was I had that picture with the colours in and so on. What that was just for fun. I thought it'd be interesting to. One day I sat out on graph paper and drew a linotype font for all of the characters, and then tried to make it as small as possible, and then I encoded it, stored it into some constants in a program, and used it to do the sort of comparison bitwise between, like, we fantasize these fonts essentially. It's kind of like reverse OCR. But what we did when we overlaid it, we get as like a percentage match, but we then trained that percentage match to predict the other count. So the other count was based, on the statistics of letters, transformations, edits. So we used this second thing as an independent predictor of it, and then we weight the two. We put the two things together with a slight down weighting to the one that's just based on the pretend bitmap.
Thank you.
Any other questions? There was one. Yes.
It's very good result, but my question is, does the original OCR use the language model?
Sorry?
Does the original OCR use the language model? If it has a language model, I think it should.
Oh, yes,
produce
it
a
does
bit
to some
better
extent
result.
use a language model. That's true. But our language model is by no means redundant because we're using 5 grams, we're using entity lists, we back up, we get a cost of any word, even, including words which are not in our dictionary, because we just keep on backing off. We have a list of rare words, we have a list of special words, we have sort of entities, and like the extra little details in producing an actual practical product, like there's an awful lot of them. And in the end, they finally back off to character 4 grams, so that any word has a cost, and that enables us to, in fact, I wish I'd spent more time on one of those slides there. There's a slide, you know, where you pick the path like this. You would notice there that our language models enabled us to say, we're not going for this word which is sort of the real word, which was, you know, the thing delivered us. We're going to say that it wasn't that real word, it was another one, sort of thing. And also, one of the words, there were 3 different spellings of it. And the reason for that is because we used basically a dirty corpus. We trolled the dirty corpus to build our lexicon. We melded other things in with it, and we could have filtered it out. We kind of left it in to see what happened. And basically what happens is it always picks the most common thing. And in fact, guess what? The most common word is usually what you'd call the correct spelling. Now, this is for a limited time period. So what people were talking about before about historical variance mightn't apply. You should really do it focused on a particular corpus. And then you can vary it for...
Yes, right in the back.
What is the hard stuff?
Beg your pardon?
What is the hard stuff for your engine? Where do you not succeed? What
Oh,
are
the
mistakes?
hard stuff is,
Yes.
is the one that had those the language tree and the little circles and things like that. And basically what that was doing, it's doing the naive way to do it is to get a word that you're interested in finding possible suggestions for, get a great big dictionary, test every single word, and to see how close it is using that character confusion matrix. But that would just take forever. So you have to do something a little bit smarter. But nevertheless, it does take most of the time, but we're really happy with it because it actually works. And it gave us those things. I mean, to me, it was almost unbelievable. We got those things with up to 8 errors. And it guessed the right one. And didn't need the help of any language model apart from, you know, this process. And it guessed it as the top suggestion. So, you know, we're incredibly happy about it. But it's the thing that consumes all the CPU. But, you know, we've written it to run pretty fast. It's, you know, it uses threads. And we used to be assembler programmers once, so we're kind of into doing things efficiently. And we could make it faster, but hardware's cheap, isn't it? But it runs perfectly well on you know, ordinary grade Commodore Garden servers.
Okay, I think we have time for one more short question.
One other question I had. What OCR engine or program did you use for your before applying your?
Which OCR engine did we use? We used the Abbey Finery, or we used the most common one. Actually, there was one minor thing we noticed about that. When we have conversations about this and we tell people, they usually say, why don't you use the spell checker, etc. And then people who know a bit more say, well, hang on, couldn't the OCR engine tell you? It's got a flag in there which says whether it had high or low confidence. And we thought, yeah, this would be great. It'd give us a real leverage. But in fact, it doesn't really tell us much, because we finally figured out that what it really says is this character has not many features in it. Like, it was always like a dot or an I or an O. We're given strangely high confidence. And it's the complete opposite in reality. They're the things which, turn into other stuff. So we tried to fiddle around with it mathematically to get something out of it, but essentially we gave it up. And especially because if we change to a new version of Abby or something, they'd have a different algorithm, and just too hard.
Okay. Thank you. Let's thank the speaker again.